Hello again. This is the second video on chapter 11, and I hope you're doing well. Let us get started here. All right. So what I'm going to do, I'm going to continue with the section that we were working on, and we stopped at test for homogeneity. So far we did test for independence, where we had just a table, right? Contingency table. We had a variable here and a variable here, and we had a bunch of cells here, right? And we had to find the expected value in each cell and then compare that to the observed value that we are given, and then calculate our chi-square number, test that, figure out degrees of freedom, which was number of rows minus 1 times number of columns minus 1, and then find our p-value and make a decision. We did that for test of independence. So let's talk about this test for homogeneity. So in test for homogeneity, what we are trying to do is very similar to what we did for independence. In fact, the calculations are exactly the same. So we have a table, contingency table, but this time we have populations, maybe several populations or two or more, and then we have a categorical variable with different levels. And the question we want to answer here is can be used to draw a conclusion about whether different populations have the same distribution or not. So this test only tests whether the population have the same distribution. We don't actually figure out what kind of distribution they have. We just want to know whether they're the same or not. So the way it works is we write the null hypothesis as, so basically these are different levels of the variable. So a null hypothesis says that these levels are basically the same for the three populations, or whatever number of populations we have here. So for example, here it says L1 at P1 is the same as L1 at P2, the same as L1 at P3. And then here the second row says L2 at P1 is the same as L2 at P2, same as L2 at P3, and so forth. So these are hypotheses, and the alternative hypothesis says that that at least one of these is not true. At least one of these is not true. Okay, so that's the idea of this test. So how does this work? Or we're going to talk about it and see. Okay, so let us start. So again, suppose here that data were sampled from three populations, and assume that the categorical variable had three levels, and we talked about that. To find the expected values in the cells, we use the same procedure as independence, right? Remember, we put it in a matrix, and the calculator actually finds the values for us. So it's the same. If you want to do it by hand, it's the same way. You have to find the grand total and find the probabilities and multiply, right? We did that in previous section. Okay, so so the requirements for this test are that let me get the pen. I've got the pen. There you go. So all values in the table must be greater than 5 or equal to 5, so greater than or equal to 5. And the common uses are comparing two populations, for example, men versus women, before versus after, east versus west, and so forth. So the variable is categorical, and with multiple possible response variables. So here is an example. So these are college students with different preferences on living arrangements. So the question is, are these two populations basically have the same distributions, or do they have the same distributions when it comes to choosing living arrangements? So that means, does it matter whether a student is female or male in terms of picking what kind of living arrangements they like, whether they live in a dormitory, an apartment with parents or other? So that's the question. Well, we have observed values here, right? So we're going to calculate the expected values here and then compare them and find our chi-square distribution. Chi-square test stat and go to the distribution to find the p-value. Okay? So suppose 250 randomly selected male college students and 300 randomly selected female college students were asked about their living arrangements, and the results are in this table. So do male and female college students have the same distribution of living arrangements? Well, what we're going to do is the same thing we did with independence, right? So we go to calculator and create a matrix, right? So we're going to create a matrix. Let's say here is, so what we are going to put in the matrix is, first of all, the size of the matrix would be 2 by 4, right? 2 by 4. So we are going to go to matrix and then go to edit and make this one 2 by 4, and then put the numbers in there in order right there. So we want to put 72, enter, and then 84, enter, 49, enter, 45, enter, and then 91, enter, and 86, enter, 88, enter, and 35, enter, right? So make sure, let's see, make sure we have the right matrix. So let me quit, go back to matrix, get matrix A and enter. Yes, and these 2 decimal places I changed to 2 decimal places, so you can go to mode and change back to float. This way you could just get numbers with no, if they don't have decimal place, it doesn't show it. Okay, so now we have the correct matrix. Let's check, make sure we have the correct numbers. It looks like it is. Yes. Yes. Okay, now we're going to run that test. So the test is stat tests, and it's called what? It's called chi-square test, right? Pick that one. Now observed values obviously in A, we just put them in A, right? And the expected will be calculated and put in B. So let's calculate. So the p-value is 0.017 and our test stat is that. That means if you were to calculate the expected values here, and 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 then subtract them, square them, and divide by expected value, and then do the same thing for every cell and add them all up, you would get this number. So 10.12. And the p-value for that is 0.01. So at 5%, at 5%, we are not gonna we're going to reject because p-value is smaller than what? Smaller than alpha. Okay, so that's how we do it with the calculator. Of course, you could do this by hand like you did before, but that would be a lot of arithmetic that the calculator does for you. Okay, so again, the null hypothesis was that the distribution of living arrangements for male college students is the same as the distribution for female students, and the alternative hypothesis says the distribution of living arrangements for male college students is not the same, right? So in this case, our value is, our p-value is 0.0175, and is smaller than alpha. Our degrees of freedom is found the same way. The number of rows minus 1 times number of columns minus 1. So number of rows minus 1 times number of columns minus 1, so it's 3 times 1 is 3. So if you were to do this with a table, then you would have to go set up what? Set up a rejection region. And since this is 5%, you would have to find a number from the table that has 5% to the right of it. And those numbers are given in tables like this one, right here. So you see degrees of freedom, and these are how much area is to the right of the number. So for degrees of freedom of 3, we go 5% to the right, so it's 7.815. Now we know our test stat is what? Is 10 point something, right? So if you bring that, you see it falls in the rejection region. If you were to do this with rejection region, that's how you would do it. Okay? All right. Now, the conclusion is that at 5% level of significance from the data, there is enough evidence to reject the null hypothesis, or saying that to conclude that the distributions of living arrangements for male and female college students are not the same. Remember, the null hypothesis said that they were the same, so we reject that. All right, so this is called the test of homogeneity. And the last thing in this chapter we want to do is just take a look at comparison of what we have done so far. We did goodness of fit test, right? A goodness of fit test, the null hypothesis says that the population fits the given distribution, and the alternative says that it doesn't. So it used to test whether a population with unknown distribution fits a known distribution. So somebody says, when somebody says expected values, that means what? Let's say the expected values are these numbers. What they mean by that the whatever we are taking samples from matches this distribution. And we, of course, we take a sample and we get the observed values and we test that. So that's the goodness of fit test. And the next one we did was test of independence. And the null hypothesis in this case says that the two variables are independent, and the alternative says they're not. So it's used to test whether two variables or factors are independent or dependent. And we did that, and remember we did contingency table, right? And we used the calculator here. And that was chi-square test, right? That would find the cells, the expected value for the cells, and then find the p-value for us. And the third one we did was test of homogeneity, which is basically comparing populations and see if they have the same distributions or not. So the populations follow the same distribution is the null hypothesis. The alternative says that at least one of them is different. And again, we do this similar with the same setup, similar to independence tests, right? We use chi-squared test on the calculator, gives us the p-value, whether we reject or fail to reject. And now we're going to do another test, and this test is about somebody claims that, let's say we have a population and somebody claims that they know sigma squared or sigma, right? So somebody claims that they know one of these. Then we take a sample of size n. We're going to find either s squared or s. And then from the sample, we're going to do the test. Now, how does this work? Well, remember in central limit theorem, when we took samples and found x bar, the x bars created a distribution we called normal, or t, depending on whether we knew sigma or not. Now here, these numbers also make a distribution. So s squared and s make a distribution. But what we do to them when we get this number, we're going to do this to it. We're going to multiply it by n minus 1 and then divide by that sigma squared that is hypothesized. If it's sigma, we square it and put it here. If it's sigma squared, we just put it here. So, so what we do here, we get this number, and this number is our chi-square. So that's our test stat. Then we come to test the distribution and see where this thing falls, or we find p-value, or we do rejection region, right? So let's, it could be, this test could be left tail, right tail, or two tail. So it could be the situation where we have a population and then we take samples of size n, we find s squared or s, we do this to it, right? And then these are our chi-square. So if you keep taking samples and find chi-square, the chi-squares make a distribution, of course, is chi-square distribution. And now, if our test is right tail, somebody says, for example, let's say the null hypothesis and alternative could be that, let's say this says that sigma squared is, less than some number, right? Some number. So this one is going to say what? Greater than or equal to, or just equal to, right? So this is going to determine that our test is left tail, right? It's going to be left tail. So depending on the null and alternative hypothesis, we're going to have three different tests, right? A right tail, left tail, and two tail test. So what we do, basically, we're going to use chi-square distribution, and degrees of freedom is n minus 1. So we take our chi-square distribution, chi-square test stat, and then bring it over here, and then find the area to the right of it, that's p-value. Or maybe if it's left tail, find this, that's the p-value. Or if it's two tail, maybe it's here, we find this and multiply it by 2, because it has to be on both sides, right? So that's the idea of this test, and we can easily do it. So it says that the FCC conducts broadband speed tests to measure how much data per second passes between a consumer's computer and the internet. As of August 2012, the standard deviation of internet speeds across internet service providers was 12.2%. Suppose a sample of 15 of them is taken and the standard deviation is calculated. An analyst claims that the standard deviation of speeds is more than what was reported. So the reported was that So basically what we have here is somebody says that this is greater than 12.2, right? So the null hypothesis is going to be, we could just put equal to, or you could put less than or equal to, doesn't matter. So this is a right tail test, right? So the way it works is, we're going to take this number that comes from the sample. That's our what? That's our S, is not S squared. I mean, it's not S squared, it's S. So remember, what do we do? What do we do with that number that comes from the sample? Is S. And remember, our formula was what? N minus 1 times S squared over sigma squared. And that right there is sigma, so we have to square it here. This also is S, so we have to square it. This is our chi-squared number, and we're going to bring it here. Is a right tail test. Put it here, wherever it is, find the p-value. Right? So let's do that. So here we go. This is degrees of freedom, of course, is 14. It's the sample size. The sample size was 15, right? Right here you see it, 15. So chi-square would be 15 minus 1, right? And then this number has to be what? 13.2 squared, because it's supposed to be S squared. And this is supposed to be sigma squared. And our number is 16.389. So we put it there. It's a right tail test. And find that p-value. And it's easy to find the p-value, right? Is chi-square CDF, right? So let's do that with the calculator quickly. So we go to second distribution, and then we'll go to chi-square. Let's find it. Is right there, chi-square CDF. And then we put 16.39, comma, 10 to 99, and comma, 14. There. So it's about 29%, the p-value. So that means we are not going to have enough, we don't have enough evidence to reject that, right? So the p-value is that, so we decline to reject the null hypothesis. There's not enough evidence to suggest that the variance is greater than 12.2 squared. All right? That's how we do test of variance or the standard deviation, doesn't matter. Okay, so that we got to the end of this chapter. This video is shorter than the other one, so I'm going to come back here and again say bye to you. Take care of yourself and others, and I'll see you in the next video, which is chapter 13. Okay, and take care.